Ralph, can you hear me and see the screen?
Yeah, I can hear you. And yeah, I can see the slides.
Okay.
Professor?
Yeah.
Just out of curiosity, do you think taking a class in spectroscopy would be useful if we're going into semiconductors?
What kind of spectroscopy?
There's just like a chemistry class called like Elements of Spectroscopy. It's part of the like minor in material science. I was just wondering like what your take on that is.
Spectroscopy is a very broad field. So some types would be useful, but in general, probably not, because in chemistry, they do things like NMR and stuff like that, which isn't particularly relevant. No, I think you're better off taking courses in quantum mechanics or solid state physics.
All right, thank you.
Mm-hmm. Good morning. I'm going to quickly review what we started with about BJTs on Monday. And the initial part of the discussion will be tested on in the exams, okay? And I'll tell you when you go to the more advanced parts where I'll not test you, but there will be a problem on the first part, okay? All right, so BJTs are an application of p-n junction theory, except that we have two p-n junctions connected back to back. We have emitter base junction that's typically forward biased, that's connected back to back with a collector base junction that's typically reverse biased. Okay, that's my base, that's my emitter, that's my collector. Now, to understand the physics of this, we started first by looking at just one p-n junction, and we focused on the reverse characteristics. Well, this is the IV, the I saturation times e to the power QV over KT minus 1. So if it's reverse bias, you get a constant voltage independent current of minus I sat, which we know, of course, is governed by the thermally generated carriers because of black body radiation, which creates this intrinsic carrier constellation Ni. And this current is independent of voltage, even if I increase the reverse bias, because it's a supply limited current. You have very few minority carrier electrons on the p side, few minority carrier holes on the n side, and when they diffuse to the junction, they're swept right across. But the rate at which they're swept across with increasing field does not matter. It's a supply of the minority carriers that matters. Okay? But then if I increase the supply by having an extra source of radiation, for example, shining a laser with an energy, photon energy h nu greater than the band gap, I can create extra electron hole pairs. That's my optical generation rate. And those carriers which are within a few diffusion lengths of the reverse bias p-n junction would now be contributing to the leakage current, okay? Now this is a very important device that we'll discuss next week. It's one of the important optoelectronic devices, a so-called photodetector or a photodiode. And clearly it's useful because you get a current which is proportional to the light shining on it, okay? Now we'll set that aside for a second, and we said that, okay, really what we're talking about in some sense is some sort of a hole injector, say, in this case on the inside because of light absorption. But let's postulate some hypothetical hole injector. And if I have more holes injected as minority carriers on the inside, I'd get more leakage current. Same thing, I could have electrons on the p side, okay? But we'll ignore that for a second, because in a typical BJT, the emitter, which is p plus in this case, is assumed to be very highly doped, and most of the current then is because of injected minority carrier holes on the n side, okay? Now that expression is of course given by p-n junction theory. So the excess hole concentration, delta PE at this junction, I'm calling it delta PE because that's the excess hole carrier concentration in the base at the emitter base junction. I'm calling the delta PE, would be given by P sub n, the starting value, which is Ni square over Nd, Nd being the doping in the base, times e to the power QVBE over KT. Okay. Now we normally have a -1, but in forward bias you can ignore the -1. Okay. So this is my excess carrier concentration at the emitter base junction. All right. But since I've created an excess carrier concentration over here compared to in the bulk of the base, of course there'll be a diffusion of the carriers from the high concentration region to the low concentration region. And hopefully remember from chapter 5, that will then give rise to a decaying exponential e to the power minus x over LP, okay? But that of course was true only if it was a long diode. In other words, the base width was very, very long, where you ignored the growing exponential term, right? Because when you solve the continuity equation, you have not only a decaying exponential, you also have a growing exponential term. But for a long diode, because this blew up, we ignored that. But now the diode is not going to be a long diode. It has to be a narrow base diode. So we will have both terms in the expression for the carrier concentration in the base. That's what we will see. Okay. So not only will we have a decaying exponential, but we'll have a linear combination of a decaying plus a growing exponential term over here. Now at the other end of the junction, the base collector junction, we can assume that the excess carrier concentration goes to 0. Okay, so the delta PC is approximately equal to 0 because this junction, the collector base junction, is assumed to be reverse biased. Now this mode of operation is known as your normal active mode of operation, where this emitter base junction is forward biased, you inject carriers, and the collector base junction is reverse biased so that you can collect the injected carriers across a narrow base. Okay. Now we'll see later on today that you don't necessarily have to operate a BJT like that. I mean, you're free to forward bias both junctions or reverse bias both, or maybe forward bias the collector junction and reverse bias the emitter. In other words, you're now forcing the collector to act as an emitter and the emitter to act as a collector. That's known as the inverted mode. And all those modes are used in digital logic. Okay, but let's start off with the most common mode, which is the emitter base junction forward bias, and that's forward bias, and the collector base junction is reverse bias. All right. And because this junction is reverse bias, delta PC equals 0. All right. Now, if you look at the equivalent circuit, a very simple model seems to be that I have a diode, the emitter base diode, that's connected back to back with a collector base diode. Okay. Now, based on that, then let me ask you a question. Could I then make a PN junction, could I then make a BJT by actually taking a diode like this and connecting it with a wire with another diode like so? Would that act as a BJT? Anybody?
No.
No. Very good. And why is that?
Because the base that you're relying on a thin base, a narrow base to diffuse across, and you got a wire in between.
Yes, that's exactly right. Okay. So it's not just two diodes connected back to back. These two diodes have to electrically interact, as Branch said, by having a narrow enough base so that the injected carriers can be collected by the collector junction. Okay. In fact, even if you didn't have a wire, if this base width was very wide meaning much wider than the diffusion length of the holes in the n-type base, that also would not act as a BJT. Okay, so you have to have a narrow base, narrow compared to the diffusion length. So that's a key point. All right, so then we looked at the main components of the current in a BJT. Once again, in the normal active mode. So I'm assuming this is forward biased, this is reverse biased. And once again, it doesn't have to be like that, but this is the usual mode. So it's a normal active mode of operation. So as you can see by how fat these arrows are, the dominant current component, that's a useful one, is this whole current, the minority carrier whole current in the narrow N-type base. And because it's narrow compared to the diffusion length, hopefully most of them survive the diffusion journey across the narrow base and are then collected as collector current IC across the reverse bias collector base junction. Okay. Unfortunately, however, not every injected hole does survive the journey. Some of them can recombine with the electrons in the base. And of course, if you lose some of the holes and they recombine with electrons, you have to replenish those electrons in the base as base current. That's my component 4. Plus, the other component of the base current is, because this junction is forward biased, not only do I inject holes this way, unfortunately, I also inject electrons that way. And why did I say unfortunately? Well, this component of the back injection of the electrons, which, by the way, contributes to current this way because electrons have a negative charge. But anyway, these injected electrons clearly cannot contribute to the useful output collector current, right? So that's bad current, that's a bad current, okay? But you're kind of stuck with those, okay? And that'll kind of limit how much current gain you can get. Now, there are 2 parameters that we define based on this. One is the useful output collector current, IC, divided by this component, only the whole component of the emitter current, IEP, and that is known as the base transport factor, okay? Now, that will be determined basically by how much recombination losses there are in the narrow base, okay? Now, in a well-designed device, it'll be close to 1, but not exactly equal to 1, okay? 1 is sort of your highest possible asymptotic limit if there's no recombination losses. The other important parameter is what fraction of the emitter current is useful current, okay? And that is defined as IEP divided by the total emitter current, which is IEP plus IEN. That is known as your emitter injection efficiency gamma, okay? Now, you'd also want that to be as high as possible. Asymptotic value would be 1. How do I make it as high as possible? I make the emitter very, very highly doped, okay? Now, if I make the emitter doping highly doped, is that going to increase this current? No, that will reduce this current, right? Because remember, the current depends on Ni square over Na for this component, and this current depends on Ni square over Nd in this direction. So once you have that, then you can define some circuit parameters, which are known as the common base current gain, alpha, which is sort of in this mode of operation where the base is assumed to be common between the input loop and the output loop. It's known as the common base mode. Now, that's generally not a very useful mode because if that's the way I define it, my output current is IC and my input current is IE, okay? And we just saw that that ratio cannot be, it has to be less than 1, right? In fact, that ratio called alpha is found to be the product of B, the base transport factor, times gamma, the emitter injection efficiency. Okay, how do you get that? Well, let's start with the definitions of base transport factor and gamma, and the rest is very simple algebra. Hopefully, you looked at after class on Monday. So let's look at the definition of alpha, which is IC over IE, which is written as IEN plus IEP. IC is written as B times IEP. So this works out to B, the base transport factor, times IEP over IEN plus IEP, which is gamma. Okay, so alpha, which by definition is this ratio, works out to the product of the base transport factor times the emitter injection efficiency. Now, both B and gamma are going to be pretty close to 1, maybe 0.9998. So alpha is also going to be close to 1, but has to be less than 1. In other words, in the common base mode, you don't really get a current gain. In fact, have a little bit of current loss, all right? But nevertheless, you can switch more power at the output terminal than at the input terminal because you get a lot of voltage gain in this mode. So it's still an active device, all right? Now, in most circuit applications, you'd like both voltage gain and current gain, and that can be achieved by this so-called common emitter mode of operation, okay? As shown in this circuit over here, where the input is applied between the base and the emitter, and the output is measured between the collector and the emitter. So it's the emitter that is common between the input loop and the output loop, okay? So now my input current is going to be not IE, but it's given by IB, right? While my output current, of course, is IC. Now in this mode of operation, that's known as the common emitter current gain beta, and this can be very large, 100, several hundred, okay? Because now it's IC, the output current, over IB, the input current. Rest is very straightforward algebra. You just plug in the expression of IC, which is B times gamma, and IE, use KCL, because IB must, of course, be equal to IE minus IC, right? By using Kirchhoff's current law. So with that, algebra 101, you'll see beta works out to alpha over 1 minus alpha. Alpha is a number that's close to 1, say 0.99. If we see that beta can be close to 100, if that's the case, okay? So you can get a lot of current gain. Now, if you look at the physics, I've always found this to be kind of a little bit bothersome, because in the common base mode of operation, it almost looks like that the base current is sort of an afterthought, if you will. In the sense, what I mean by that is, here I'm injecting emitter current, and a fraction of that current is lost via recombination, and then there's a tiny amount of backflow of the current, okay, and that's my base current, right? And IE and IC are very large numbers, say, and IB, which is the difference of IE minus IC, should be a tiny number, obviously, right, by KCL, okay? And then it becomes a little bit hard to understand from a physics point of view why controlling this tiny amount of leakage in the base can allow you to modulate a very large current in the collector, because that's what I'm saying, right? It's kind of like, I get a great big fat pipe, and there's a tiny leak, say, in that big fat pipe. That's my emitter, that's my collector, and the tiny leak is my base. What I'm saying is, by controlling that leakage current in the base, I can modulate a huge amount of current flow from the emitter to the collector, right? I mean, that's basically what I'm claiming in terms of the common emitter current gain, right? I hope you get the question that I'm asking myself, right? Well, the physics of this is explained in the book, and the short answer is, as I modulate my tiny amount of base current, okay, if I dial it up or dial it down, that will modulate the charge stored in the base, and that will then modulate the base potential, and therefore that can modulate the base emitter voltage. And a small amount of change of the base emitter voltage then can have a huge change on the emitter current, okay, because you have an exponential dependence of this delta PE on that small value of changes of delta VBE, okay? So that's why the tiny base current can modulate this humongous emitter and collector currents. All right, now, before I leave this slide, I want to talk about the charge control approach of solving the same problem, okay? In the charge control model, in p-n junction theory, remember we said that we could solve for, let's just look at this p-n junction, say, okay? So we are able to solve for this current first by looking at these carrier distributions, and then we took the slopes of the carrier distribution. That's my diffusion current, right? And we got the slope on this side, and that was one way we calculated p-n junction IV characteristics. But the second way we calculated it was look at the total stored charge, which I'll call QB, say, in steady state, all right? And then we saw if the recombination lifetime was tau, these carriers are being lost at a rate QB over tau P, and then you have to replenish the current carriers at the same rate. And that's why I got an expression for the emitter current. Remember that? Well, we call that the diode current, but here that would be the emitter current. So I have a steady state distribution of excess carriers that are lost at a generation recombination rate of tau P, and therefore you have to replenish it at the same rate. So that's my expression for the current, right? So that was a charge control way of calculating current in a diode. Well, you can apply that same kind of principle to the BJT now. where this is my stored charge in the base. And suppose I'm looking at a steady state DC current. I have to maintain a steady state charge distribution QB, which will be nothing but the integral under this distribution divided by the lifetime. All right. That will give me an expression for component 4 of the current, right? Because that's the rate at which carriers are being recombined and I have to replenish them at the base. So that's this component 4 of the base current. That's not component 5, right? That's a different physics. That's the back injection. Here I'm looking at the recombination losses. All right, so that's my base current component 4, okay? Which is the same as component 1 over here, right? Because 1 equals 4. You guys with me? All right, but how about the useful collector current, IC, this component 2? I mean, that's really the most important output current, right? Now you can think of IC using a charge control model as the steady state base charge distribution QB, which is this integral under this more or less triangular distribution, divided by another time constant, which is called the transit time, tau t. Don't confuse that with tau p, which is the generation recombination lifetime. Tau t is known as the transit time, and it is the average time it takes for the carriers to diffuse across this narrow base. All right. Now we haven't really gone through the details of that, but it'll turn out to be transit time is related to the diffusion length square, dp square, divided by the base width. Okay. I didn't prove that, but we can kind of take that for granted. Okay. So depending on the diffusion coefficient and how narrow the base is, that'll determine how long it takes on average for the carrier to diffuse across. Okay, that's known as your transit time. If that's the case, I can then immediately calculate an expression for beta, not the base transfer factor B, but beta, the common emitter current gain, which is defined as IC over IB as QB over tau T divided by QV over tau P. So that will work out to tau P, the lifetime, divided by tau T. Okay. Now in this, I have made an approximation. I've ignored this back injection of carriers from the base of the base, from the base into the emitter. So I've ignored this component 5. If I ignore component 5, what am I assuming about the emitter injection efficiency? Anybody? If I ignore component 5, I'm ignoring this component, right? So then I'm assuming gamma equals 1, which is clearly not true, of course. So this charge control expression will be an overestimate of the actual beta, right? Because I've assumed that gamma is equal to 1. Okay. Anyway, so the charge control way of calculating the beta is shown over here. This is assuming that gamma equals 1, which is not true. So this will always be a overestimate, okay? Because gamma is never going to be equal to 1. It's going to be close to 1, but it'll be slightly less than 1. All right. Now, typical values over here in a BJT in the common emitter mode are shown over here. Okay. So then I'd get a beta of this. So if I have a beta of this, in this circuit, I can figure out how much input current flows, which is the input voltage, 5 volts divided by this load resistance. Okay. Now, how about the resistance over here? Well, because this junction is forward biased, you can assume that the impedance of the forward bias diode is pretty close to 0, approximately. So this is an approximation of the base current, and then you get the collector current, which is beta times that. Okay. So that's how much current will flow in the output circuit. Now, the way you make these BJTs is described in the textbook. This is a simplified version. This is not exactly how you make them in practice today. That's a more involved approach that's described in the book. You should read through that, but I'll not make you responsible for that in the exam, okay? But the simplified version is quite easy to see. So on the left-hand side, you see the top views of the structure, and on the right-hand side, the corresponding cross-sectional views. So suppose I start with an N-type substrate. So here I'm looking at not a PNP BJT, but an NPN, okay? Which is the normal way you make the BJTs because electrons have higher mobility than holes, okay? So in this case, I'll start with an N-type substrate. You grow an oxide. Oxide acts as a diffusion mask for the dopant. Then you etch a window in it. you implant or diffuse a p-type material in there, so that'll form your base. Then you grow another oxide, you etch another smaller window, and in that you put in the emitter n-type doping, which is n plus emitter, okay? And then you form oxide window on top, you etch contact holes, and then you put a metal contact finger to the emitter, a contact finger to the base, and in this case, you could assume that I'm making the collector current contact at the back, okay? Once again, this isn't the way actual BJTs are made in industry, but it kind of gives you a sense. So a couple of important points. Clearly for the BJT to work, this emitter window, which is the smaller window, has to be nested entirely within the larger rectangle, which is the base window, right? Plus, when I make this emitter junction, you need to get it as close as possible to the base collector junction so that the base is very narrow, but you don't want it to go all the way across, right? Because then the emitter is getting shorted to the collector. Similarly, suppose this emitter rectangle gets very close to the base rectangle. In the lateral dimension, you get a breakdown, right? So you have to have the emitter window nested within the base window, okay? So those are the things that are done in a very clever way, in a self-aligned fashion, in a practical way of manufacturing BJTs that's described in section 7.1 of the textbook. All right, now the next part, I'm going to mathematically derive expressions for the base transport factor and the emitter injection efficiency. Pay attention to this very carefully because I will give you final exam problems where you have to solve these, okay? And I can guarantee you that it won't be simply plug and chug. You really have to understand the physics behind this, okay? Otherwise you'll not get the solutions, okay? All right, so to come up with expressions for B, not beta, B the base transport factor, and gamma the emitter injection efficiency, let's look at a P BJT. This emitter base junction is forward biased, okay? And therefore the depletion region is kind of narrow, okay? And this is reverse bias, so the depletion region is wide. Not only that, I'm assuming that the emitter is doped more heavily, so the depletion region is shown to spread less on the emitter side than on the base side. Okay, so the reverse bias at the collector base junction is VCB, and the forward bias at the emitter base junction is VEB. All right. Now all the action is in the base. Because this junction is forward biased, I'll have a high concentration of carriers over here. I'll die down as a sum of a growing exponential and a decaying exponential. So it's not just a decaying exponential term, e to the power minus x over LP. Sorry, e to the power minus x over LP. But also you'll have a growing exponential term with different constants C1 and C2 that have to be solved for with appropriate boundary conditions, okay? What are the boundary conditions? You can assume that delta PC is approximately equal to 0 because this junction is reverse biased, okay? It's actually not 0, it's actually minus delta, it's minus n sub, sorry, it'll be actually minus p sub n, right? The minority carrier whole concentration in the n-type base, but approximately 0, okay? The delta PE, on the other hand, will be large, okay? In fact, it'll be approximately equal to Ni squared over Nd in the base times e to the power Q VBE over KT minus 1, okay? But you can kind of ignore the minus 1, okay? Because if I have forward bias, the exponential term dominates over there, okay? So that'll be your delta PE. Okay, so that's my delta PE, while delta PC over here is approximately equal to 0. All right, so I'm interested in looking at the DC steady state current, okay? So I have to solve the steady state carrier continuity equation, and we had gone through that solution at the end of chapter 4 as a worked out example. And since this is a second order differential equation, the solution will be in terms of a growing and a decaying exponential with these constants C1 and C2, which, like I said, have to be solved by applying the appropriate boundary conditions. The boundary conditions are at x equal to 0, which is this junction. The carrier concentration is equal to delta PE. If I put in x equal to 0, that's nothing but C1 plus C2. While at this junction, suppose I have a base width of WB, I plug in x equal to WB, x equal to WB. So I have the two terms, e to the power WB over LP, e to the power minus WB over LP, times C1, C2. That's my delta PC, which is approximately 0, right? So I have the two boundary conditions at x equal to 0 and x equal to WB, all right? Now, if I have two equations, clearly I can solve for these two constants, C1 and C2, right? Two simultaneous equations. Straightforward. The algebra is very straightforward, but the expression looks messy, all right? And I'll show that in the next slide. But just before I show that, this shows the band diagram of this PNP BJT. Well, let me draw it over here. So that's my P plus emitter, N-type base, and P-type collector, emitter, base, collector. Initially in equilibrium, the Fermi level has to be constant everywhere. And then with respect to that, I can draw the band edges. So in the P-type base, the valence band's closer. In the N-type, sorry, in the P-type emitter, the valence band's closer to the Fermi level. In the N-type base, it's the conduction band that will be closer, but not as close because the emitter doping is assumed to be higher than the base doping, okay? And then in the P-type collector, once again, EV is closer, okay? But in reality, EV won't be quite as close because typically the collector doping will be lower than the emitter doping. So this is just an approximation. That's an equilibrium. Now let's look at the normal active mode of operation, where this junction is forward biased. So if I forward bias the junction by VEB, I reduce the barrier, the built-in junction potential over here, okay? And I reverse bias this junction. So I have a large reverse bias across the collector base junction, okay? So the way the device works then is I inject holes from the P-type emitter into the emitter, all right? They diffuse across this narrow base and they appear over here. Now, as far as this junction is concerned, these are minority carriers in the valence band of the N-type base, right? And they're swept across. So that's how I'm increasing the supply of minority carriers at this reverse biased collector base junction. And they get swept across and are collected as collector current, all right? So on your own, you should try to draw the band diagram for an NPN, okay? See, it just gets flipped. All right, so now that I have the expression for the carrier distribution in the base, excess carrier distribution in the base, and I know in principle at least how to solve for C1 and C2 by solving these two simultaneous equations. I can plug that in and come up with the expression for delta P, right? And that's what I'm showing over here. As I said, the algebra looks messy, and I'm not going to go through every single step. I strongly, strongly urge you to solve on your own these two simultaneous equations, get C1 and C2, and then plug that back in over here to convince yourself that indeed that is my expression. Okay, so you can kind of see what the terms are. So that's my decaying exponential term with C1, and then the growing exponential term with C2. Okay, or maybe I had it the other way around. Yeah, the growing exponential term with C1. Yes. All right. Now, because you have both growing and decaying exponentials, all the expressions are in terms of hyperbolic functions. Okay, so just to refresh your memory, cosh is e to the power y, e to the power plus e to the power minus y over 2. Sinh is e to the power y minus e to the power minus y over 2. Once you have these, then you can get all the other hyperbolic functions. So for example, cotangent hyperbolic. Cotangent hyperbolic would be cosh over sinh and so on and so forth, okay? The other thing that we'll do in solving these BJT problems is recognize that y is going to be a small number, and therefore you can do a Taylor expansion of these exponential terms to simplify the math as appropriate, okay? Why is y a small number? Well, this y is WB, the base width over the diffusion length, right? And that, as I said, has to be a small number because I need a narrow base compared to the diffusion length, right? Otherwise, I don't get a high performance BJT. So these exponentials will have an exponent y, which is WB over LP, which has to be a small number for the BJT to work properly. And therefore, you can, in many cases, simplify these hyperbolic functions by using Taylor series expansion and so on and so forth. All right, so with that background, let's see if we can figure out what the base transport factor would be. All right, so what I'm showing is the overall distribution, okay, which will be more or less a triangular distribution shown by the straight line, except that it will have a slight droop to it, okay, because of recombination in the base. All right, and this solid line will be a linear combo of this decaying exponential plus a growing exponential with appropriate values of C1 and C2. Okay, so once I get the linear combination of this decaying and growing exponential, I'll get more or less a triangular distribution, but with a slight droop to it. All right. Now, once I get that distribution, I'm home free because I know how to calculate diffusion currents, right? What is the expression for a diffusion current? Well, JP, let's look at IP, diffusion is equal to dP dx, that's a concentration gradient, times the diffusion coefficient dP, but with a minus sign because stuff flows from high to low concentration region. That gives you the whole particle flow per unit area. To get the current due to that, I have to multiply by the whole charge, which is plus Q, therefore the minus sign stays put. That gives me the current density JP. To get the total current, I have to multiply by the cross-sectional area of the diode, right? So I have to multiply by whatever the cross-sectional area is of the diode. Remember that? So if I know what the P is, well, actually, I can write that as delta P, okay, because the background constant value never matters. I have an expression for the delta P. So all that I need to do is take the derivative of this with respect to X, and then plug in X equal to 0 to get this current, and X equal to WB at this point, right? Now, if I do that, at this point, what current component am I getting? That is clearly IEP. If I get the gradient at this point, what current component am I getting? That's clearly IC, right? Let's go back for a second, make sure that you're with me. So what I've gotten is, I've gotten this more or less triangular distribution, where it's got a slight droop to it because of these recombination losses, right? Then I'm taking the gradient at this point. That'll give me IEP, not the total emitter current, right? Because I'm not solving for this IEN, this back injection of electrons, right? I'm only looking at the whole current component. So that's just IEP. Similarly, if I take the gradient at this point, that'll give my collector current. So the ratio of the two slopes will be my expression for my base transport factor, B. You guys with me? As I told you, I will test you on this in the final exam, okay? And you need to understand the physics. You can't just plug and chug because the problem will be tricky. You won't be able to do that, okay? All right, so if you do that exercise by taking the gradients, you see, you end up getting these expressions over here. So the important one is once you take the derivative, you see that the LP appearing in the denominator, right? Because you have e to the power minus x over LP. If I take the derivative, the LP appears in the denominator, okay? Here I've still left it in terms of C1, C2. I can plug that back in over here. I'd strongly urge you to go through these algebraic steps on your own. It's very straightforward, except that the expressions look messy because unfortunately you're now dealing with growing exponential and the decaying exponential term. So you're left with all these, you know, funky cotangent hyperbolic, all these hyperbolic functions, all right? But then you can come in and do the Taylor series expansion in many cases. So for example, secant hyperbolic, you can look to that, approximately is equal to this by just keeping the first order Taylor series term. Okay, so that's an approximate form of the base transport factor. Now, I can guarantee you, like I said, if I give you an exam problem, you won't be able to just apply this approximation. Okay, you have to really understand the physics behind the thing. All right. Now, once I get IEP and IC, the difference of the two currents will give you the base current, which is QP over the lifetime. Is that the total base current or only part of it? Anybody? Let's go back to our master figure. So if I calculate IEP minus IC, that takes care of the recombination losses, right? So which part of the base current does that correspond to? Anybody?
Are you asking for the number, like 4?
Yes, that's what I was asking for. Yeah, that's component 4, okay? Because IEP minus IC is this component 1, which recombines with component 4. Very good, okay? This does not take care of the back injection component 5. So that brings me to the emitter injection efficiency. And let's see if we can figure that out, okay? All right, so this is an expression for the emitter injection efficiency. And you should think of this as a worked out example, if you will, okay? Because I can change the assumptions and you get totally different expressions. Okay? So once again, very important that you get the basic concept, okay? And that is, the basic concept is emitter injection efficiency, by definition, is IEP over IEP plus IEN, right? So depending on the parameters of the problem, you have to figure these out, and that's how you define the emitter injection efficiency, okay? So in this case, I assume that my diffusion length in the emitter for the back injected electrons is very, very short. ln in the emitter is very, very small, okay? Now that's generally a good assumption because the emitter is assumed to be very highly doped, okay? If the emitter is highly doped, any back injected minority carrier electrons will meet this large concentration of background majority carrier holes and recombine very, very rapidly, right? So that's why I'm just showing the decaying exponential term, okay? Here also in principle, I'd have the decaying exponential term plus a growing exponential term, e to the power plus x over ln, if this emitter region was narrow compared to the diffusion length of electrons in the emitter, right? But because it's highly doped emitter, ln is going to be short. Therefore, by definition, this emitter is going to be a wide emitter, and I can ignore the growing exponential term, okay? So by doing so, for the emitter current, I just retain the decaying exponential, then I take the gradient over here, and if I take the gradient, the ln appears in the denominator, right? You should recognize the rest of the terms. It's exactly like that in a PN junction, right? Okay, so that's how you get it. Okay, so you get delta PE now, okay, which will have, so delta PE will be Ni squared over Ne, the emitter doping, e to the power QVBE over KT, okay, minus 1, but you can kind of ignore the minus 1. So that's what I have over here, okay? So NP is Ni squared over Ne, okay, times the diffusion length, because I'm looking at the diffusion current, okay? So now it's Dn, obviously because of dP, times Q times the area of the device, okay? So Q times area of the device, sorry, Q area of the device Dn over Ln times this term over here. So that's my IEN, all right? How about IEP? Well, for the IEP now, let's assume that it's a perfect straight line, okay? If it's a perfect straight line, IEP is this concentration, which is this, okay, divided by the base width, okay? So if that's the case, I'll end up getting if you simplify for the cotangent hyperbolic, you'll see that will be basically proportional to 1 over WB, okay? I haven't shown that over here. So this is a full-blown expression, but if you look at cotangent hyperbolic, which is cosh over sinh, okay? For low values of y, what do I get? Cosh for small values of y is equal to what? It'll be e to the power, say, close to 0, or 1 plus 1 divided by 2. So cosh should be equal to 1, while sinh y will be approximately equal to y, right? So cotangent of this will be approximately equal to 1 over y, right? So you'll end up getting this is approximately equal to LP over WB, okay? The LP will cancel with this, so you'll get something basically divided by WB, and that makes perfect sense because the gradient is this concentration divided by WB. You guys with me? All right. So once I get that, then I'm home free because then the total emitter current is IEP plus IEN. And then by definition, gamma is equal to IEP over IEP plus IEN. Okay. Simple, messy algebra, but it's simple, straightforward. Come with an expression for this. Now you can then rewrite it in terms of the conductivities, it turns out, okay, because if you look at these expressions, you end up getting expressions in terms of the diffusion coefficients. Now the diffusion coefficients can be related to mobilities because D over mu equals KT over Q by the Einstein relationship. And then you get ratios in terms of mobilities, and then ultimately relate that to the conductivities because sigma equals Q mu, so sigma n will be Q mu n times n, and similarly sigma p will be Q mu p times p. Okay, so that's how you end up getting these conductivity expressions. All right. Now, I'm not going through every single algebraic step, and honestly, the best way to understand the physics is to reproduce the algebra on your own. Okay, it's very straightforward physics. It's just that the expressions are a little bit messy. All right, and I really want you to do that as a homework problem, just for your own sake, so that you understand the physics. Because once again, if I will give you a problem in the final exams related to B and gamma, where I'll change the assumptions where you can't simply use these expressions, right? This is just a worked out example, if you will, okay? So how could I change the problem? So, well, before I do that, if I have this assumption now for the gamma, can anyone tell me what I have by default assumed for the base transport factor B? Anyone? Don't confuse this B with the base, by the way. Okay, that's base. That's my base transport factor. If I have a straight line, as shown over here, what value of B am I getting? B, by definition, is IC over IEP, right? IC is given by the slope at this point, while IEP is given by the slope at this point, right? So if it's a straight line, obviously B is equal to 1. Yes, very good. Okay. So in that sense, you know, this assumption is a little bit contradictory with the assumption that I made over here, but then, you know, it's pretty good approximation, right? So then essentially what I've done in these worked out examples, in some sense, I've kind of independently calculated B, where I can't assume it to be a straight line, right? Because then I'd get B equal to 1. So here I take into account the droop, but then for the emitter injection efficiency part, here I assume it's kind of like a straight line, and then you can combine the two and take the product of the two to get alpha equal to B times gamma, and then beta becomes alpha over 1 minus alpha and all that, okay? So these are all approximations, okay? Let me change the problem statement another way, and let me see if we can figure that out. So now, if I assume that my diffusion length in the emitter is not very short, as shown over here, but very long, or alternatively, if this emitter width is very short, how this whole derivation change? So as shown over here, I'm assuming that the emitter width is much wider than the diffusion length, right? What if the emitter itself was also very short compared to the diffusion length?
Would it also have a linear gradient?
Excellent, very good. So instead of just having decaying exponential as shown over here, that will also be a linear profile, okay? So then the emitter current, IEN, would be this concentration divided by the emitter width, okay? This is a typical problem. I think in the homework I've given you a problem like this. And one favorite way of mine to trick you guys is to give you too much information. All right. So in this particular example, I've given you parameters in the not all parameters, emitter, base, and collector. And the trick for you is to figure out which of these parameters are relevant. Okay. So as an example, if I am interested in the diffusion length in the emitter, this, by the way, is a PNP, right, as seen over here. So the diffusion length in the emitter, I have to look at the lifetime in the emitter, right? So I have to pick this term. And DN, so I have to pick this term, right? So, look through it carefully. So I know if you pick this example, for example, that would be a wrong answer, right? So to solve these problems, you have always to go back to the basic physics. And if you do it that way, you'll never go wrong. If you blindly try to use this formula, I can guarantee you I'll change something in the problem statement where you can't use this formula. All right. Okay, so everything that I've talked about up to this point is fair game for the exams. Okay, so this is the 0th order treatment of the BJT. This is DC behavior in steady state in the normal active mode of operation. So study this part very, very carefully. Okay, what I'm discussing from now on for the rest is more advanced aspects of BJTs. Don't shut me off and start watching Netflix on your iPhone now, okay? But I will not test you on this in the exams, okay? It's important stuff, but because BJTs, like I said, have kind of fallen out of favor and MOSFETs reign supreme, kind of keep this at the back of your mind, but I will not test you on the rest of the BJT stuff in the exam, okay? But no, don't ignore me completely. All right, so what are some of these more advanced aspects of BJTs? Well, one of them is this idea of generalized biasing. What that means is, so far, I've assumed that the emitter-base junction is forward biased and the collector-base junction is reverse biased. So that's this dotted line. Okay, that's my distribution in the base. But, if I have a BJT structure, there's nothing preventing you from forward biasing the collector-base junction and reverse biasing this junction, right? If I do that, that's your so-called inverted mode of operation, okay, which is given by this. So that's my normal mode of operation, and that's a so-called inverted mode where the collector is forward biased and the emitter is reverse biased. So in other words, I'm making the collector behave as the emitter and the emitter behaves as the collector, right? So that's the so-called inverted mode of operation, while this is the normal mode of operation. Now let me ask you a question, hypothetically. If I chose to operate the BJT in the inverted mode, do you think the gain of the device, current gain of the device, would be higher or lower in the inverted mode? To understand that, you have to go back to the structure of the BJT, okay, and look at the doping. So now my collector is acting as the emitter, right? While the emitter is acting as the collector. And keep in mind that the emitter doping is very, very high, while the collector doping is very, very low, right? So if I was to use the actual collector as the modified emitter in the inverted mode, what do you think would happen to the emitter injection efficiency?
Would it decrease?
Lower injection of holes?
Yes, very good, okay? Because if my emitter doping is low, I'd get a lot of back injection of carriers into the emitter, right? And therefore my emitter injection efficiency would go down and my gain would go down, right? So you can use it in the inverted mode, but that's not a smart way of doing it, okay? However, in digital circuits, in the past, at least when people use BJTs for digital circuits, sometimes you have to invert the thing when you want to turn the transistor off, et cetera, all right? So anyway, in this generalized mode then, you can write down the current as a linear combination of the normal mode of current plus inverted mode. So that's my normal mode component, okay? So that's my diode expression, okay? And then, but then, in the inverted mode, you get an inverted mode alpha, while this is the normal mode alpha that I've been talking about, okay? So my collector current was my base, was my common base current gain alpha times the emitter current, right? But then if I was to bias the collector base junction forward bias, you get a diode current, which works against that. Similarly, for the emitter current, that's my normal emitter current for the forward bias junction. And then if I was to operate in the inverted mode, I get this, okay? So I get a linear superposition of these currents. So this is captured by a famous model for BJTs known as the Ebers mole model, after the two physicists who derived this, okay? And the equivalent circuit is shown over here. So between the emitter base, you have this forward diode, back to back with this collector base diode, as I've mentioned, all right? But if you think about it, that by itself doesn't capture all the physics, right? Because if I just had two back-to-back diodes, that doesn't capture the interaction between the emitter and the base by having a narrow, doesn't capture the interaction with the emitter and the collector by having a narrow base. How do I capture the interaction? That's captured by these current sources, right? So in the normal mode, when I forward bias this junction, this emitter current, a fraction of that alpha n, appears as collector current, right? So that's a current controlled current source. I get a collector current IC, which is controlled by the emitter current times an alpha n. So this is a very key part in the Ebers mole model, in the normal mode. But like I said, you could also operate in the inverted mode. So you get a current controlled current source. So that's my collector current times alpha I, the current gain in the common base current gain in the inverted mode, this way, right? So this is your equivalent circuit in the so-called Ebers mole model, okay? But the usual way, as I said, is you forward bias this. So you have this component and you have this component, and you reverse bias this. So normally this doesn't matter. This is a small current, okay? It's just a leakage current, okay? So that's a key part of the picture of the Ebers mole model, okay? And based on that, then you can, solve any circuit problem where, one junction is forward biased, the other is reverse biased, or maybe both of them are forward biased. So examples of those are shown over here. So if I was to forward bias both junctions, right? So I get this dotted line, plus I might choose to forward bias this junction. So I get this dotted line. So the overall distribution in the base is shown by this blue line over here. If that's what I did, if I forward bias both junctions, the BJT is going to act as a short circuit because the base region is flooded with carriers, and that's going to be short circuited, okay? So that mode of operation, you can see what's going to happen. So if I forward bias this and forward bias this will have a low impedance. They'll have a low impedance. This will basically be a short circuit, okay? Now that corresponds to this region of the output characteristics. So I'm plotting IC as a function of the output VCE for different base currents, IB, okay? Now it kind of looks like the MOSFET output characteristics, but of course it's a different device altogether, right? So in the MOSFET, it was ID versus VD for different gate voltages, but here now I'm looking at the collector current as a function of collector emitter voltage for different base currents, okay? Now if I was to forward bias both junctions, what is my VCE magnitude going to be? Well, if this junction is forward biased, that's a small number. That junction is forward biased, that's also a small number. And the VCE is actually the difference of these two forward biases. Therefore, VCE is going to be very, very small, okay? And in this regime, as I change these forward biases, you have these forward currents which are fighting each other. So you can get a lot of change of the collector current for small changes of delta VCE, where delta VCE is VCB minus VBE, right? The two diodes are working against each other. Now, what is the impedance of the BJT under these conditions? Is it high or low? Well, impedance, or say resistance, in a normal resistor would be defined as V over I, but these are all voltage dependent resistors. So you have to define that as delta V over delta I, right? So is my impedance high or low under these conditions? Delta V is very small and I get a large delta I, right? So this is a very, very small number. or the conductance, which is the reciprocal of that, is a very large number. So it's almost like a short circuit. Okay. Now this mode of operation is known as saturation. The BJT is said to be saturated, which is a little bit confusing at times, because remember, in the MOSFET, this part of the characteristics, ID, VD, is what we call saturation, right? So that's what we call saturation. And this we call linear. But in a BJT, this part is known as saturation. Okay. So in the MOSFET, the saturation region had a large output impedance, while when you use the term saturation for a BJT, that actually has a low output impedance. Okay. Just terminology. Now you can solve for all of these generalized biasing modes using the charge control model over here also. Okay. I'm going to go over this quickly. So this is the normal mode charge distribution QN. QI is the inverted mode charge distribution. Okay. Then you can solve for the currents. So for example, in the normal mode, we saw that the emitter current is equal to the sum total of the collector current, which is normal mode distribution, divided by the transit time in the normal mode from the emitter to the collector, plus the recombination time. So tau t is the transit time, while tau p is the generation recombination lifetime. Okay, so that's my base current over here. So that's my collector current, IC, plus I. So the first term is IC, and the second term is IB. Okay, that's IC. That's IB, okay, in the normal mode. But you could also operate the thing in the inverted mode. So now it's QI over tau t in the inverted mode. And that, okay. Now all of this is the DC part. But this model can also be extrapolated to the transient part, as we did in the case of a diode. So if there was a transient problem, the charge distribution could actually go up with time. Okay. In other words, the charge distribution is in steady state, it keeps going up with time, say. Okay. If the charge is going to keep going up with time, I'm having trouble with my pen for some reason. So if it was going to keep going up its time, my pen's not working very well. Anyway, that then adds this term over here, right? Because you have to pump in more current to allow the charge distribution to go up with time. All right. So anyway, that's how these charge control models are determined, and from that you can come up with expressions for the common base current gains in the normal mode or the inverted mode, and so on and so forth. All right. Now you can look at other modes of operation. So for example, if you reverse bias both the junctions, what's going to happen to the base charge distribution? So now my emitter base junction is reverse biased, and the collector base junction is also my pen stopped working, sorry, my apologies. So anyway, both junctions are reverse biased, so you can see that both at the emitter base junction and the collector base junction, the delta PE and the delta PC are close to zero. It's not exactly zero, it's actually minus of the starting values, minus PN, which is the minority carrier whole carrier concentration in the N-type base. But the bottom line is, in this case, the transistor will act in the high impedance mode, so-called cutoff. The transistor is cut off. In saturation, the transistor is a short circuit, while in cutoff, the transistor is going to be an open circuit. So that's the kind of thing that you do in the case of a digital circuit application of a BJT. Okay. Yeah, so this shows, as I'm forward biasing the junction more and more on the right-hand side, you see that I'm flooding the base with a lot of carriers, shown by this dark blue shaded region. That's when the transistor will be in a short circuit mode, while on the top, I'm showing it in the cutoff mode, but because I've swept carriers away from the base by reverse biasing both the emitter junction and the collector junction. All right. Any questions? All right. Now, So that's sort of the basic analysis of the BJT. In the exam, you'll not be responsible for the Ebers mode model and all these complicated charge control models. But for the graduate students, you might want to read up on it. It's very interesting physics. The physics of a BJT is actually more complicated than the physics of a MOSFET, if you think about it. Okay, because you have two diodes back to back, a lot of complications in the problem. So one such complication is illustrated over here in what happens in a practical BJT. So if I was to make a BJT, as I illustrated at the beginning of this class today, you'd start with a certain type of a substrate, you'd implant or diffuse the base dopant shown as N sub D, okay? Then you open up a smaller window and then you implant or diffuse the emitter dopant, the Na as shown over here, it's a higher level, okay? And then the base width is this region between the two junctions, right, as shown over here. Now you notice that if you make the diode this way, the base doping is not uniform, right, as a function of depth over here, or as a function of position between the emitter and the collector. In fact, the base doping decreases from the emitter junction towards the base junction, right? Now, if I was to approximate that not as a curve like this, which is curving upwards, but just to simplify the math, as an exponentially decreasing function as shown on the right hand side, okay? I choose that approximation because I can then come up with a simple analytical formulation, okay? What impact does this variable base doping have on the transport? Well, if I have base donor concentration varying as a function of position as shown over here, that means I have more holes. I'm having a hard time explaining because I can't, my pen stopped working. Maybe it's, my hole concentration in the, my electron concentration in the n-type base is seen to be higher at 0 than at WB, right, as you see from this curve. Which means that even if I didn't apply any bias, the holes would tend to diffuse to the right, right? Because I have more holes on the left-hand side than on the, I misspoke. This is PNP, so I'm looking at electrons in the base, okay? So I have more electrons at x equal to 0, which is the emitter base junction, than at WB, which is the collector base junction, right? So the electrons would like to diffuse to the right. But of course, if the device is just sitting there without any biases applied to it, there cannot be any net current flowing, right? So there has to be an opposing drift current. But because these are electrons, for the opposing drift current, the electric field has to point to the right, right? So that's my built-in potential, if you will. Now, if my electric field points to the right, now turn your attention to the injected magnetic area holes from the emitter into the base. So I have electric field pointing to the right, or in the figure, in the cross-sectional view on the left-hand side figure, it's electric field pointing downwards, right? So now if I inject holes from the emitter into the base, does this electric field help the motion of those electron holes or hinder that? Anybody?
Helps them.
Helps them. Very good. So if it helps them, would the transit time between the emitter to the collector go down or go up? It'll go down, right? And if the transit time goes down, if you look at the charge control model, for example, if the transit times go down, what would happen to the collector current? It would go up, right? If I get a higher performance BJT, it'll have a higher gain. Okay. So in this worked out example, I've assumed an exponentially varying concentration profile, even though it's in practice it's not going to be exponentially varying, because if you have an exponentially varying profile, you can come up with a simple analytical expression for the electric field. In fact, I believe I had given you a homework problem in chapter 3 here to solve for this built-in electric field. And although this electric field opposes the minority carrier motion in the base, opposes the majority carrier motion in the base, it actually helps the minority carrier transport, and therefore the transistor performance improves. Okay. Switching gears, another second order effect that you see in a BJT is what happens with increasing collector base reverse bias. So as shown by this lightly shaded region, that's a depletion region at the collector base reverse bias junction. As I increase my collector base reverse bias, or in other words, as I increase output voltage VCE, this depletion region is expanding more and more into the neutral base region, right? Under those conditions, then, the charge distribution, pen's dying, is going to go down to 0 earlier and earlier, right? Because the neutral base region, which is this dark shaded region, becomes narrower and narrower. If that happens, what happens to the gradient of this charge distribution with increasing VCB? Obviously, it gets steeper, right? And if it gets steeper, the collector current would increase. And that's what's shown on the right-hand side. So with increasing output voltage, with increasing output VCB, the neutral base region shrinks, the gradient of the minority carrier distribution becomes steeper, and therefore the collector current goes up. Now, this is reminiscent of an effect that we discussed for MOSFETs. Does anyone remember what that is? What does it kind of look like? Looks like DIBL, drain-induced barrier lowering, right? Of course, the physics is different over here. It's somewhat similar. It's the depletion region starting to interact more and more. Okay, this effect is known as the early effect, not because it's early versus late, but after the physicist James Early, who first identified this. Okay, and it's a bad effect. Okay, because once again, that means that the output impedance would go down, which is not a good thing from a circuit point of view. All right. Now, if you keep increasing the output voltage by VCB or VCE in the common emitter mode, okay, at some point you'll find that the collector current not only increases but actually goes up dramatically. Okay, the transistor breaks down, and the reason it will break down, say the common base mode is easier to understand. The reason it will break down is as my base collector voltage increases more and more. Then we have seen from p-n junction theory, the device can break down due to impact ionization or avalanche breakdown, right? Because of the very high electric fields. How about tunneling breakdown? Is that a possibility? No, it's not a possibility in this context, because for tunneling breakdown, remember, you need a very narrow barrier, right? Which then requires a very high doping on both sides of the junction. You need a P plus, N plus junction. But typical collector dopings in a BJT are not high. They're low because you don't want the base collector to break down under reverse bias, okay? So the depletion regions are going to be too wide for tunneling breakdown. The breakdown is going to be due to impact ionization or avalanche breakdown, okay? And then depending on the mode of operation, you can define breakdown voltages BVCBO. And the way to read that is, it's a breakdown voltage between collector and base with the emitter open, okay? And that'll break down when the impact ionization rate M, multiplication rate, goes up to infinity. You can similarly define a BVCEO. So this is the breakdown voltage between the collector and the emitter with the base open. So the O stands for open, okay? If the base is open, my base current is equal to 0. Under these conditions, IC must be equal to IE. And if you go through the math, you'll see that BVCEO is going to be smaller than BVCBO, okay? Any questions? All right, let me wrap up our discussion of BJTs by sharing a few thoughts about equivalent circuits, okay? So I'm looking at the cross section of a BJT, and what's shown over here are the series resistances in the base region, which I call RB. Okay. Now the impact of that is when I apply a base emitter forward bias, these are cross-sectional views, and the base current flows, clearly there'll be a IR ohmic voltage drop because of the base current flowing. Okay, so in the central part of the device, not the surface region, because of this IR voltage drop, the forward bias will actually be smaller than near the surface region. It's kind of the same kind of effect that we talked about in the case of a MOSFET, where the source drain series resistance weighs some of the applied drain bias, right? So here, it's a similar kind of effect, right? You have a parasitic series resistance in the base, and therefore when you apply a VBE at the surface between the contacts shown between these dark metal contacts, in the interior of the transistor, because of this IR voltage drop in the base region, the effective VBE will be smaller. You guys with me? All right, so if that's the case, where would I get a higher emitter current density? Well, clearly it'll be at the surface region, right? Because that's where the effective base emitter forward bias is the highest. This effect is known as emitter current crowding effect. And it's not a good effect because that causes local heating in the surface region of the transistor. And there's second order effects that I haven't gone into. You basically get high level injection effects as we discussed for diodes, and the overall BJT gain would suffer. Okay. So the way you solve this, mitigate this problem, is you lay out the transistor by breaking up the emitter into multiple fingers as shown on the right-hand side. And you have these interdigitated fingers for the emitter contact and the base contact. And basically the idea behind this is you force the current to be distributed more uniformly across the whole device rather than all crowding in a narrow region in the top of the device, as you have on the left-hand side where you did not do this interdigitated finger arrangement of the emitter contacts and the base contacts. This leads to my final slide, which is the equivalent circuit of a BJT. Now, remember, the idea behind equivalent circuits of semiconductor devices is you have all this complicated physics of drift, diffusion, etc., etc. But then you want to sort of capture as much of the physics as important in terms of simple lumped circuit elements like lumped resistors, capacitors, and we did examples of that for the MOSFET, but you can do similar things for the BJT. And a simple version is shown in figure A and a more complicated version in figure B. Okay, so the idea is the more of the physics you want to capture, more of these lumped circuit elements you put in that you can then put into your circuit simulators such as SPICE if I'm going to do circuit modeling. Okay, so the 0th order model shows the base resistance between the base contact and the device that we just talked about, but then you'll also have a collector resistance RC. But if you notice, I'm not showing an RE. Any guesses as to why? That's a good approximation.
High doping?
Very good. The emitter is assumed to be very highly doped, so it's the most conductive. Okay, so there'll be an RE, but it'll be much smaller than the RC and the RB. All right. Then I'm also showing these capacitances between the base emitter junction. These are the depletion capacitances that we discussed for diodes, and similarly we have a collector depletion capacitance. Okay, so that's sort of a very crude model. A more elaborate model is the one shown in B down below. Okay, where I once again show these capacitances and resistors as before. Okay, but now I'm also showing the voltage controlled current source. That's the most important part of it. Okay, the top one didn't show that. It just showed the resistors and capacitors. But this GM times VBE is my collector current controlled by the base emitter forward bias. Okay, so that's the transconductance GM. I mean, that's the guts of the device, right? I mean, that's what I'm really after. But then you have a whole bunch of other parasitic capacitances and resistors in the structure. I'm not going to go into that, but that's it's got a colorful name. It's called the hybrid pi model. Okay, why pi? It's kind of like the Greek symbol pi. If you drink a lot of beers and squint your eyes and all that. Okay, it doesn't quite look like pi, but Kind of looks like the letter pi. So it's anyway, it's known as the hybrid pi model. All right. So next week, I'll wrap up with a few loose items about BJTs and jump into optoelectronics. Any questions? All right. See you next week.